direct stiffness method, simplified approach. So we have discussed direct stiffness method for continuous beams as well as plain trusses so far. Okay, so for continuous beams, we have somewhat simplified approach. Another approach, first I mentioned about this simplified approach to you, but we didn't thought of taking this one. But later we thought this will be better if you go for the non-sway frame analysis. Okay, so this is another approach. Actually, we have taken that means 2 degree of freedom per node element we have considered, and we have formulated K metrics for this like this 1, 2, 1, 2, and 3 and 4 like this, and we have by hearted a 4 by 4 matrix, 12 A bale cube, 6 A bale square like that. To 4 by 4 matrix we have by hearted, and according to that alone we have done the problem. And this is somewhat simplified approach. Here we'll be considering only rotation alone at the ends. Okay, so for that case, the KE matrix is EI by L into 4, 2, 2, 4. So that 4 terms only come into action. Okay, so is it okay? This, I think this element stiffness matrix we have discussed. I think so. This is a simplified. So this is a element with 2 degrees of freedom, 1, 2 at the ends. So for that case, the KE matrix is like this. So if you get a problem like this, A, B, C, D, this 10 meter, there is no load here. This is 36 kilonewton. I think this problem we have done for the analysis. Additional probability. Anyway, I've done that problem again using this simplified approach. So here also the steps are the same. Kinematic indeterminacy or degree of freedom is taken as 2. The structure coordinates when you define. In the previous problem, we'll take 1, 2, 3, 4, 5, 6, 7, 8 like that. We'll define. Here there is only 1 degree of freedom per node. 1, 2, 3, and 4. Okay, and accordingly the element coordinates you can write. Then element stiffness matrix is somewhat easier. So in the previous case we have to write 4 by 4 matrix for each case. Okay, so here we can write only 2 by 2 matrix, 1, 2, 1, 2. So when you take member AB, it's only 1, 2. Member BC we have 2, 3, and member CD we have 3, 4. Only the kinematic intensity that we are having is theta B and theta C alone. Theta A is arrested and theta D is arrested. We have only theta B and theta C. Okay, that is 2 and 3. D2 and D3 are the only unknowns or degree of freedom. Okay, and KE of AB, when you write EI by L of AB, length of AB into 4 to 2, 4. You can easily get the KE of AB, then KE of BC. You can take only rotational load. You may substitute the length, then find KE. Then here also you can number. It is 1, 2, 1, 2. Then this is 2, 3, 2, 3. This is 2, 3, 2, 3. And here it is 3, 4, and 3, 4. So you can arrest the degrees of freedom corresponding. So 1 is arrested. 2 and 3 are remaining. Here also 4 is arrested. Only these three term remaining. Here all the 4 terms are remaining. 2, 2, 2, 3, 3, 2, and 3, 3. All the terms are remaining. You may add all these to get the structure stiffness matrix. So when you add this one, this 0.4 plus 0.33, 0.73 you will get here. Then here and here it is 0.167 alone. 2, 3, and 3, 2. And here you will have 0.33 plus 0.33, 0.66 as the last term. So this is for 2 and 3. Here it is 2 and 3. So now you go to step 3, the structure stiffness matrix K. Okay, and the same procedure follows for the equivalent joint load. Then P0 and PF. P0 minus PF, there is no nodal load, so P0 is 0. And PF is the fixed end moments. You can find the fixed end moments along the rotation direction alone. So the moments are alone. There is no need to find the reactions. Okay, so these moments you can find and accordingly. So in the first span, there is no load. So the PF value is 0. The second span, I found it as 60 for anticlockwise, WAB square by L square and WAB square by L square. Here it is 64 and 32. It's minus 64 and plus 32. This is anticlockwise and this is clockwise. Okay. So for CD also you can find the PF values. This is minus 240 and this is plus 240. And PF of the entire structure, you can delete the arrested degrees of freedom and add the remaining. So you'll get for 1, you'll have 0 plus this 1 is 0, this you can cut. For 2, we have 0 and minus 64. So the net will be minus 64. Here for 3, we have plus 32 and minus 240. So it will be minus 208. And this you can cut. Okay. So this is the net PF for 2 and 3 corresponding to 2 and 3. And P0 minus PF. P0 is 0, 0 minus PF is the net P, 64 and 208. Now you can solve K into D as P. K, you know, D is D2 and D3, you will get D2 and D3 as a matrix. Now the final step is PF plus KE into D. PF is for AB plus KE of AB into D of AB. D of AB means D1 and D2. D1 is 0, only D2 remaining. You can substitute the value and find MAB and MBA. Here you will not directly get the shear force. You will get the bending moments alone. Bending moments at MAB, MBA, then here MBC, MCB, and here MCD and MDC you will directly get. Then how will you draw the BMD? You can easily draw the BMD by the free bending moment diagram you can draw, and the fixed and bending moment by marking these values MAB, MBA, MBA. Like that's minus, this is plus 3.306. You can mark it plus 30. Again, this is plus and this is minus. Like that, you can mark and you can find the salient values of this free bending moment diagram and draw the BMD. Okay, and in order to find shear force values, you have to find the shear force, the net shear force like this. So the first step, so you have to mark the load. The moment you have obtained also mark like this. 3.36 clockwise, this is clockwise, this is anti-clockwise, this is clockwise positive, anti-clockwise negative, and clockwise positive. Like that you can mark the values. Okay, so due to the external load, there will be some shear force, and due to the net moment change, there will be some sort of shear force. Okay, so here it is 3.3 clockwise and 6.613 clockwise. There is 9 point something clockwise, 9.9 clockwise net moment is there. So there should be an anti-clockwise moment of 9 point divided by the span. The span is 10 meters. So that is 0.992 is the shear force here. So is it okay? 0.992 point. So what will be the net moment by this shear force? 0.992 into this span. That is 9.92. That is acting anti-clockwise and this is clockwise. So that will be counterbalance. Balance each other. Okay. And when you take this one, there is a 36 kilonewton load here. So you can find the reaction 24 and 12 by you can take each one separately and you can find 24 and 12. And find this is the shear force due to the loading. Okay, and due to the net moment here it is minus 6.613 and 137. So the net moment of 131, around 131, divided by 12, that is 10.897 is the shear force, and that should also be anti-clockwise. This is anti-clockwise and this is clockwise, and this you have studied in STA2, I think. That's why I'm going too fast, and if you have any problem you can contact me personally. Okay, and here also the total load 20 into 12, that is 240 kilonewton is acting downward, that is 120. Since it is symmetric, 120 and 120, that is due to the load. And the moment also, this is 137 anti-clockwise and 291 clockwise. There is a net moment of 291 minus 137. That divided by span should also act anti-clockwise. So this is upward and this is downward. So this will produce an anti-clockwise moment of 12.879 into 12. Okay, so that will be balancing each other. And you can find this as a total moment shear force here, this as a total shear force here, total shear force here. Like that, you can take the value and draw the shear force value. Is it okay? Is it clear? This is another simplified approach in which we are taking only rotation alone at the ends of the beam.